This is using Desmos now to find out the intervals of increase, decrease, and max and mins, your properties of graphs. So we're going to plug this function into our calculator, and eventually we will learn how to graph these very quickly without using Desmos. So f of x equals, and then let's do this again. So f, and then I just use the little keyboard here. So if you don't see it, it's right down here. Open the keyboard of x equals, and the absolute value is right there. So we can go back and look at what we have. X plus 2 minus 5. So x plus 2, and then you just scroll out. X plus 2, and then scroll out, minus 5. And there's our graph. So now we don't even need everything else that's around there. I can just get rid of axes, axis numbers, even the grid completely gone. We don't care about that. All again we need is that local min. And we know an absolute value looks like a v. So we just need that local min. So that is what we're going to graph on our little picture. So -2, -5 with that v shape. And then I like to put the point. So -2, I already forgot it. It was -5. Yep. I should have known it says right there, -5. All right. So again, this is our increase. Let's do n just to save some time. Increase, decrease, max. And again, it's absolute max in this case, or absolute min in this case, and min. So intervals of increase, we know it's going to go up from here and down this way. So we can say that it is increasing from -2 to infinity. And remember, we focus on the x value because that's what is affecting our graph, and it's decreasing from -infinity to -2. So our x value is going from -infinity to -2, and our x value is going from -2 to infinity. Now max, there's none, because again, for max we need increase, decrease, and what we have is decrease, increase. So we have decrease, increase, which makes this a min. So our -2, -5 is our min. So translating that, we say x equals -2. We have a min of -5. And again, this is an absolute min because it is the absolute lowest point. And so that's all we're doing. We're plugging it in, drawing a picture of it, and plotting our point. Let's try our next one. So you don't even have to even put an m. You can just put y equals. And then it's 0.05 x cubed plus 0.25 x squared minus 1.5 x minus 1.5. And it's very important if these numbers are wrong in any way. I've already saw one. Forgot the 5. So 0.05 x cubed, 0.25 x squared, minus 1.5, and minus 1.5. All right, there we go. So we can even scroll out and look at it. And so again, we're looking for those critical numbers. So -5.241. Let's draw our picture. It looks like this. We have a point here, a point here. There's -5.241. Yep. 6.031. 241, 6.031. And 1.908. -1.305. See if I'm right on that one. Yeah, look at that. All right, so those are our points. And then now we just have to mark it. So we know it's going to start by increasing and then increase over here as well. And then decrease. So we just need those points. That's it, just our critical numbers. So again, increase. It increases from -infinity to -5.241. It's going to decrease. We got one more, union, 1.908, comma, infinity, because that's infinity over here, because it goes that way and that one goes that way. It decreases from negative 5.241 to 1.908. And you can even see that. It's going from a y value of 6.031 to a y value of negative 1.305. And so now we can do our max and min. So we have a maximum value here because it increases and then decreases from of that, which means we have an x equals negative 5.241 with a max of 6.031, and we have a min of 1.908 and negative 1.305. So our x is 1.908, and with a min of negative 1.305. Now these are local min and local max because, again, that's an absolute min, but that's just locally min. Max. Our max is actually going to go off to infinity, which means we don't have a max, and our min is going to go off to negative infinity, which means we don't have a min. There is no minimum value here, but we have a local min here and a local max there. Okay, discontinuity. So we have two different graphs here for discontinuity. What we have here is called a greatest integer function, and here we have a rational. And I love to throw absolute values in there to see what happens. So I'm going to plug this in our calculator. Let's clear this out of there. Bring the y back in. Y equals, and it started with an absolute value of x plus the absolute value of 2x plus 4. So absolute value of x plus, and then we put a little division symbol to do the fraction, and then absolute value, and it's 2x plus 4. Make sure that's right. Here it is. And then we scroll down by clicking in there, and then we put x plus 2. And we get this marvelous looking thing. Now we also need that little endpoint there, right? And that point, and that point. So what we're talking about here is a point of discontinuity. So as you see that little point go through here, presto, we now have points to move. So if you follow this A, you can see we have an x value of negative 9.9, and then it jumps. See, right there, it jumps. So what we have here are 2 points at different locations, see? And so what we call this little gap is when you have to take and pick your pencil up to continue. That is called a point of discontinuity. So as I pick my pencil up, we have a point of discontinuity. Right there's a break. It's not a point of discontinuity, see? Right there. So this gap right here is a point of discontinuity. Anytime you have to pick up your pencil, point of discontinuity. So looking at that graph, it looks like this. And so at x equals negative 2, that's this point right here. And where you can tell it is because right here, remember that's our little situation that we have here, x cannot equal negative 2. Right here. So if x was negative 2, this would be undefined. So we have, I put 1, negative 2. So we have a point of discontinuity. So our domain for this function would be negative infinity to negative 2, union negative 2 to infinity. So all those points, right off the bat, we could have just said x plus 2 cannot be 0. So x cannot be negative 2. And so you can see here, if I move it out, it should give it to me. Come on. There it is. Negative 2 is undefined. That's what we were looking for. And so there it is. And so any points of discontinuity, you would say x equals negative 2 is a point of discontinuity. All right, let's look at the greatest integer function now. So to make the greatest integer function, you just use the word floor. And then if you scroll it out anywhere, you just do it there to home, and home will take us back to that negative 10 by 10, giving us a situation. So let's look at this. As it moves through, right, we're moving our x. If you notice, it's called a certain type of function. I guarantee you can guess what that is. It's a step function, yes. So when you see greatest integer, it is a stepped function. Step function. So it's going to go from negative 3, and then right when we have 4, negative 2, it jumps up, and then negative 1, it jumps up. See? and then 0 it jumps up, and then 1 it jumps up, and then 2 it jumps up, and 3 and 4. So what is the greatest integer? So what the greatest integer is literally the greatest integer up to that number. So we tried like a little bracket with a number in there. So whatever number you put in there, negative, let's not do negatives first. Let's put 3.1. The biggest integer up to 3 is 3. And if I had 4.5, the biggest integer up to 4.5 is 4. So as you go through any of these numbers, it's always going to be 4. All the way up to 4.99999, that is still 4. It's not until you hit 5 does it become 5. So if you look at that, we're right here, see, at 4.3, the y value is telling us what the greatest integer is. So for 4.14, our greatest integer is 4. All the way until we get to 5. See, right when we hit 5, now the greatest integer is 5. And 5.14, the greatest integer is 5. Greatest integer up to 5.333, still 5. It's not until you hit 6 that it goes up. So that's what's happening here. And so if you did negative 3.64, 3.63, the greatest integer is negative 4. Well, why is that? So at negative 3.6, the greatest integer is negative 4. Because you have to think about how negatives work. If that's negative 4 and that's negative 3, then as we move through any of these points, we have not gone far enough to get to negative 3. So the biggest integer for negative 3.6 would be 4. Negative 3.2, that's still negative 4 because we have not gotten to negative 3. It cannot become negative 3 until you hit negative 3. So see, all of these are negative 4. But as soon as you hit negative 3, now it's negative 3. But negative 2.86 is still negative 3, negative 3, negative 3, negative 3, right? And so on, and so on, and so on. So the negatives, it's always a number right before. All right, so let's look at what that means. And we just have to write our steps on there. Oops. And so we're just looking for points of discontinuity. So if I say this is 1, right? What it is it's 1 up until then, right? So how that looks like is this. It's a closed dot, open dot, closed dot, open dot, closed dot, open dot, closed dot, open dot, closed dot, open dot. And the reason is, let's go back to the Desmos to look at it. Let's do the positives because it looks nicer. So if you look at it, at 2, it's 2. So it's going to be 2 here, but as soon as you get to 3, it's 3. So at 2.9999, it's 2, but right here this would be an open dot, and that's a closed dot. So it looks like this. But no matter what, if this is x equals 1, it's discontinuous. Discontinuous. And x equals 2, it's discontinuous. X equals 3, it's discontinuous. X equals 4, it's discontinuous. So our points of discontinuity are x equals an integer is all you have to write. You can say x equals k. Let's do a nice formal one. X equals k, where k is an integer. So that is a point of discontinuity because we have to pick up our pencil to get to the next point. So those are points of discontinuity. Now domain. Domain on this one is negative infinity to infinity because we don't have any values you can't plug in here. Over here we cannot plug in negative 2. Negative 2 gives us an undefined value. Right? An undetermined actually in this situation. But over here we have a jump. Right? But we can plug in 2. If you plug in 2, you just get 2. And if you plug in 3, you get 3. And if you plug in 4, you get 4. So the values exist. See, 3 is 3. 4 is 4. So it's all real numbers on this one. So just because it's a point of discontinuity does not mean it's eliminated from the domain. Okay? So you have to be very careful on those two. Domain does not mean discontinuous if it's not in the domain. If it's not in the domain, yeah, it's discontinuous. But discontinuous does not mean it's not in the domain. Okay, a little confusing, but just basically look at the picture and determine its domain and discontinuity. And breaks in graphs are points of discontinuity if you have to pick up your pencil. So even a point like this, in order for me to get from this side to that side, I have to pick up my pencil. So if I was actually drafting this and there's a hole there, I would have to pick up my pencil and then continue from there. So if we had this situation, we know that x cannot be 1 as our domain. So if you notice, right, when it goes to 1, watch it, it just disappears, see? So if I get that to 1, there is nothing there. See? It even says 1 is undefined and puts an open dot there. So for me to actually graph that point, I would have to graph this line and then pick up my pencil and continue from 1. It would look like this. So again, look for your domain discontinuities, your domain issues as well as points of discontinuity. All right, thank you.